it's probably a good idea to understand what we mean. If we look at the dictionary definition, which is what most people try and do, first of all, when they're trying to find out what something is, science, it says the science of the properties and relations of lines, surfaces and solids. Well, I suppose that gives us a bit of a clue, but it doesn't help too much in trying to understand what geometry really is. We could ask ourselves more kind of intuitively, perhaps, what we think about geometry. So if we look at these two shapes, are either of them geometrical? Anybody? The first one, you think? Wait, who said that? I think the first one's geometrical. Anybody disagree? Anybody want to suggest anything otherwise? Why do you think why do you think the first one is geometrical?
Because all sides are equal.
Because there's some sort of recognisable order in there, or?
Is it because it's a lane shape?
Oh,
So
that's interesting.
name.
That's interesting. Yeah, that's a good answer as well. Kind of, yeah, I mean, we would tend to talk about the first one as geometrical and the second one as not. But of course, geometry can describe pretty much anything. So we could have a geometrical description of the shape on the right. In fact, you had to draw it on a computer, then it would, in a CAD application or Illustrator or something like that, it would by definition have a geometrical definition, because you'd be using a series of tools like bits of circles, maybe arcs, or portions of an ellipse, or maybe B-spline curves, or whatever it was you might be, all of which are geometrically defined as tools within the software. So in fact, although we tend to, in common language, describe things that are more regular as geometrical, in fact, everything could potentially be described by geometry, including stuff in nature. So again, it's quite common for people to say that there is geometry in nature. So this is a sunflower, and inside is the arrangement of the seeds in the sunflower head, and they obviously form a kind of pattern, a kind of spiraling pattern, which actually can be analysed based on a number series, which is the Fibonacci series, a kind of additive number series. But does it mean there's geometry in nature? What do you think? Go on, what did you think? Anybody?
I mean, if you said everything is geometrical, then...
Yeah, well, maybe. On the other hand, maybe the geometry is not in the thing, but in our interpretation or analysis of it. So whereas when we're talking about shapes like that, if we were to draw them, we'd be defining it. We would be kind of, it's a kind of exercise in working with geometry as a kind of tool for setting out the shapes. On the other hand, if we were to find one of these shapes, so if this one on the right was like somebody had spilt their coffee on the table, and you were trying to, it wouldn't be that there was geometry in the coffee, but rather that you might be using geometry to analyse or to describe or to understand the shape that the coffee had formed. So arguably, in the case here, although there seems to be some organisation, and clearly there is organisation because it's a kind of natural process and has evolved over millions of years to optimise itself in various kinds of ways. There's definitely order here, but whether there's geometry or not rather depends on how you define geometry, and I would like to define geometry as the process of analysing or understanding or describing something, rather than it being a property of the thing. So neither of these shapes are geometrical, really, except when you try and draw them or describe them, and the same might be said of them. The other thing is geometry is a kind of uniquely human kind of pursuit. It's actually really about a system of logic, a system of thinking. What we mostly think of as geometry, and one of the reasons why we mostly think of things like squares, as or name squares for that matter, as geometrical, is because mostly what we use is what's known as Euclidean geometry, which was set out by Euclid in the 15th, well, actually in around 300 BC in his Elements. And it boils down to the idea that everything in geometry should be reducible down by logical steps to a few kind of unassailable first principles. So the idea is that you have literally 5 rules that are meant to be so obvious that you can't argue with them, and then everything else has to be derived logically from those 5 rules. And here are the 5 rules. A straight line may be drawn between any 2 points. Any terminated straight line may be extended indefinitely. A circle may be drawn with any given point at its centre and any given radius, and all right angles are equal. And you have to agree that those are all pretty unarguable. You can draw a line between any 2 points and so on and so on. The 5th one, however, is a little bit more tricky. It says if 2 straight lines lying in a plane are met by another line, and if the sum of the internal angles on one side is less than 2 right angles, then the straight lines will meet if extended sufficiently on the side on which the sum of the angles is less than 2 right angles, which is clearly not quite so obvious as the other ones. And in fact, way into, or much later in the 19th century, this became the subject of a lot of scrutiny by mathematicians trying to find alternative kinds of geometry by changing that 5th rule. So having other kinds of rules, you can simplify it a little bit and say that it effectively means parallel lines will never meet. But then in our perception, as it were, in our experience of the world and perspective, parallel lines do sort of meet. So, and if you were to try and check that those 2 lines never met, you'd have to keep on going for infinity in order to do so. You can never get to the point where you can demonstrate that they don't meet. Perhaps they do if you go far enough. Which is what non-Euclidean geometry is based on. Another kind of basis on which geometry is built is obviously a set of kind of principles and rules, but once again it's about kind of logically deriving properties of things, not by what you might call empirical means, by measuring them, but rather by logic, by having a consistent system of logic. So, anybody remember Pythagoras' theorem from your school days? So, the Pythagoras' theorem says that the right-angled triangle, in fact, any right-angled triangle, so a triangle with a 90 degrees in one of its corners, the square of the hypotenuse is equal to the square of the other 2 shorter sides added together. But this is a really nice example of a mathematical proof of that. So if we take 4 right-angled triangles at the top and arrange them like that, so you can see the four triangles, there they are, and they've been arrayed in such a way that the hypotenuse, the longest side of each of the triangles, forms a square. And that means we know also that the area of that square will be the length of the side multiplied by itself, won't it? That will give us the area of that square. So all of that is an area, and then we can rearrange those pieces. So down here is the same number of pieces, the 4 triangles plus the square that was in the middle. So all of this must be the same area. But now they're forming a different profile. They're forming that square and that square. And the square on the left, the smaller one, is the shortest side of the right-angled triangle multiplied by itself. And the slightly bigger square, which isn't as big as that square, but is bigger than that one, is the other shorter side, as it were, multiplied by itself. So that means the square of one side plus the square of another is equal to the square of the hypotenuse. So what's going on there is not Pythagoras measuring thousands of triangles and concluding, well, yeah, in every case the right-angled triangle always obeys this rule, but rather finding a logic that demonstrates that it's not just true for one right-angled triangle, but for every right-angled triangle. Because you can do this with any right-angled triangle. And it's not dependent on your accuracy of measurement, or how big the triangle is, or anything like that. It's about a logical set of rules. Anyway, so that's what geometry is. So now we can ask maybe where the geometry is in architecture. And a bit like the two shapes I showed you a moment ago, we have a similar kind of thing going on in architecture. We tend to think about a kind of geometrically organised geometry in architecture as something like the building on the left, which is a very highly rational plan by a 19th century French architect working in the École Polytechnique, which was a school of architecture and engineering that was based around kind of military engineering and so on, and the source of all sorts of really interesting kind of engineering stuff, which later kind of defined the nature of engineering in many ways. And on the right, you've got the Philips Pavilion designed by Le Corbusier and Xenakis for the Osaka World's Fair, I think it was. And that's clearly a kind of organic-looking shape. But if you're going to build the thing on the right, you still need a whole bunch of geometry, in the same way that I was saying that if you're going to draw that kind of wobbly shape, you need to start using B-spline curves, you need to start using bits of arc and so on. So in fact, to describe the thing on the right, organic though it might seem in its form, it requires probably more geometry than the thing on the left. So ironically, the thing that we call geometric has actually got less geometry in than the thing that we might call organic. And so there's these, put these in a kind of bigger context. That's the Durand building, and quite a simple thing to set out and to draw. On the other hand, the Philips Pavilion is a whole lot more complicated to describe. And Xenakis, who was an engineer, later famous for his abstract musical compositions, actually. If you ever get a chance, listen to Xenakis, some of Xenakis' classical music. They're really kind of challenging stuff, based on mathematics. But what he's doing here is describing that complex shape with a series of what's known as ruled surfaces. For those of you who work in 3D on Rhino or something will probably know what a ruled surface is. It's a surface that's described by straight lines. So although it's curved in 3 dimensions, it has straight lines running through the surfaces. So a hyperbolic paraboloid and so on. This is actually a kind of irregular conoid. But there's a whole lot of geometry going into that to work it out. And of course, more recently, whether you like it or not, this kind of stuff is based on a whole lot of geometry, worked through using computer tools, parametric descriptions of a form that allow very complex shapes to be described and built in architecture. Another way that geometry can manifest itself in architecture is perhaps a more conceptual way, thinking about ideas of proportion and beauty and so on. And it's quite it's a common thread running way back to the Renaissance and beyond is this idea that if you organize something with a particular set of proportions, maybe particularly in the Renaissance, they had this idea about harmonic ratios. So you know that harmonic ratios, the way they work, the kind of set of musical scales, which is based on dividing a kind of a string. Harmonic ratios would be inherently more beautiful, that you would somehow find elegance in them because they contain those kind of fundamental relationships. There are problems with this, not least the fact that in the case of this kind of analysis, this is a drawing by Le Corbusier analysing Michelangelo's building. He's drawn over the top of it these kind of what he calls regulating lines. But much as you can kind of do that, effectively what he's doing is reducing the building to a two-dimensional plane, when if you actually look at it, it kind of exists in three dimensions. And when you experience it, you see it in perspective. So it's questionable whether you would ever see these proportions, because you're never looking at the building as if it were an elevation. You're always looking at it in a three-dimensional way. So whether they're perceptible or not. Interestingly, in the 19th century, a number of kind of proto-psychologists, people like Fechner, tried to investigate this kind of stuff, like giving people, subjects, a whole series of different rectangles and asking them to rate which ones they found the most attractive. And he kind of tried to demonstrate that the golden section, the golden section, would be a more attractive proportion empirically in that kind of way. Subsequent studies have shown that he may not have been very rigorous in the way he did that study, and they haven't really been able to demonstrate that people find any particular proportion more pleasing than any other. Although we do still quite like to believe that, I think. It may be something that's kind of culturally specific. It might be to do with what you've experienced before, there might be a whole set of factors in there. And of course, well, in architecture, there's also the nature of drawing. Now, at the moment, we're in a world where we're kind of mostly working through the computer to draw things, but there was a time when to describe three-dimensional things relied on actually quite a complex understanding of how to manipulate form through two-dimensional descriptions. So did anybody study descriptive geometry in their undergrad education? It does still get taught in lots of places, so some of you might. Did you learn how to construct perspectives and that kind of thing? To cut sections through a cone? Yeah, that's descriptive geometry. So you didn't, you just didn't know. Descriptive geometry is that way of trying to work with three-dimensional objects, but through drawing, through a two-dimensional medium, which is actually quite a tricky thing. There's a kind of common misunderstanding, I think, that things like that Zaha building that I showed you a few moments ago are only made possible because of the computer. Whereas, in fact, you can look at plenty of ancient buildings where there's incredibly complex geometries, and they manage perfectly well without a computer to do it. It just tends to be a bit more labour-intensive. And what the computer's done is perhaps make it possible to design very complex buildings in a way that's just about affordable. Whereas if we had to rely on the kind of methods that they used, say, in the Middle Ages to make complex geometric buildings, it just wouldn't work because it required too many people and too much time. For example, kind of Gothic cathedrals often took decades to build and involving hundreds of people. So, but there's a kind of whole science behind the geometry of drawing, and in a way that's what I'm going to focus on in the remainder of the talk, is to mostly look at the consequences of how the geometry in drawing can actually change what we make. I should have put it in here. In fact, if I'd got time to kind of revise this a bit for this year, I would have done so. Do anybody know the media theorist Marshall McLuhan? No, you wouldn't really. 1960s media theorist. He was really famous at the time. Not that I was there, but Marshall McLuhan had a tendency to use these little kind of catchphrases, if you like. And one of the things he said about Renaissance architecture was that there was a piazza for everything and everything in his piazza, but which he meant that there was a kind of tendency for Renaissance architecture to be organised in a certain way. And of course, the thing that defined that organisation was perspective. It was about thinking about things in perspective, which was the predominant kind of mode of representation at the time. So the way we draw things actually has an impact on what we design and how we design it. So if you take descriptive geometry and those kind of complex curves and so on that can be found in parametric design, then you end up with the possibility of creating these kind of complex curvilinear forms and surfaces. So the two examples we're going to look at to examine this idea are two painted spaces, two interiors. Let's see if anybody knows any of these. Does anybody know either of them? Might stand a chance of knowing the one on the left. You might know the one on the right. Yeah.
That's not Mondrian on the right.
No, close though. You're in the right area. Are there any Italians in the room? No. The one on the left is Sant'Ignazio in Rome. It's a painted interior of a church by a 17th century artist called Pozzo. And the one on the right is from the 20th century, early 20th century, and it's by Van Doesburg, who similar to the style movement, same kind of spot in the Netherlands as Mondrian, although in fact this interior is in France, in the south of France. So we'll look at these in turn. The first one on the left is defined by perspective. The one on the right, we'll find out, is defined by a different kind of geometry. So first, perspective. Well, perspective, of course, is used in architecture for a very long time, going back to the Renaissance, to describe and illustrate spaces and forms. And by the time you get to the 19th century, there are these incredibly proficient kind of expositions of perspective drawing, including this one by Schinkel, who incidentally was, as well as being an architect, was also a set designer for kind of opera and stage plays and things. So he's kind of thinking about the world like a stage play. But this is a piece by the artist who actually painted that interior. And, well, what's this?
It's when you look up in a church.
So it's a view into a dome, you think?
Yeah.
Right. That's the easy bit. Is it? So, what do you reckon? Is it a drawing done of an existing church or existing dome? Or is it a drawing to design a dome? What do you reckon? In actual fact, it's not a drawing of an existing dome. Neither is it a drawing to plan or design a dome that might be built. Neither is it a way of communicating perhaps a proposal to somebody else. In fact, it's a drawing to work out a painting of a dome. So what happens when this becomes part of the church interior is that this calculated view perspectival view looking up into a dome actually gets painted onto the ceiling. But the key thing is that this ceiling isn't a dome. This is a flat dome. It's a flat ceiling. It's not a dome at all. It's a flat ceiling. And painted onto it is a perspective view of looking up into a dome. Which means that providing you're looking at it from the right direction, what is difficult now because it's got all dirty and, it's old. But when it was new, you can imagine this was a bright and sharp kind of painting of a dome on the ceiling. When you're standing in the church looking in the right direction, you gave the illusion of there being a dome where in fact there wasn't one. So somehow now real space and painted space are beginning to get muddled up. So representation and real life, as it were, are blurring. And that's a black and white photograph of that dome, somewhat enhanced, I think, to make it look sharper and clearer. But further down in that same church, Sant' Ignazio, is this. And this is a similar exercise in the same kind of process, where this time a whole perspective view has been projected and painted as a fresco onto the vaulted ceiling of the church. And you can see that it wraps all around these kind of bits where the window is kind of cut into the barrel. It creates these kind of funny bits of geometry, but the perspective view ignores all of that. It doesn't ignore it, but it wraps around it, so that when you look at the ceiling from the floor of the church, what you see is not the ceiling of the church, but this painted space that extends up seemingly to the heavens. I wonder if our estates colleagues can maybe quieten down a bit.
Some heated argument.
I've got something to argue about, yeah. It's probably their overtime or something. On the other hand, if you look at it from the wrong view, you get something that's really kind of weird, because it's designed...
This is a critical moment, actually.
Yeah.
The right view and the wrong view. And I'm kind of lining it up with the ideas of subjectivity, but we can discuss that later. This is why this is really interesting. You need to be positioned in the right place for your world to be correct. As soon as you step sideways into somewhere else, your world collapses.
So the whole thing is designed around kind of one privileged position, where if you stand in that spot, then you get this amazing illusion. If you don't, then it's kind of all a bit of a mess. So perspective that makes this possible has got a long history. Better just check the time, because I have a tendency to waffle on.
It's okay.
Yeah.
You can keep waffling.
The perspective, of course, on a kind of general understanding of it, is a way of kind of giving a sense of 3D in a drawing or a painting. So this is a kind of really early example. Is this perspective? What do we think? Duchamp says no. Why is it not perspective?
It kind of doesn't look right.
It's kind of
doesn't quite.
Yeah. I mean, in some ways, it contains some of the properties that we identify with perspective. In other words, things get smaller as they go further away. In some cases, but actually, it's not properly perspective, because it's not done in a consistent way. There's no... It's not like a kind of calculated view from a particular position. It contains lots of different bits of different kind of vanishing points and fragments of perspective, if you like, within its makeup, but it isn't one consistent perspectival space. And it's generally recognised that perspective was not invented till about 1410, although there's lots of arguments that actually it was in the ancient world, and there's lots of kind of possibilities that it was kind of rediscovered in the Renaissance rather than actually discovered. And the principle on which it was based was this idea that, in the top view, that in the top illustration there, that somehow if you imagined a whole bunch of lines going to object in the world and you dropped a plane in between, a picture plane as they call it, or as Alberti called it, the veil, if you drop this kind of veil in between you and the world, and captured those lines on that surface, then what it describes is like a intersection or a section through the view that you're looking at, as opposed to parallel projection, which is what we use if we're going to draw a plan or a section or an elevation, is the lines are parallel. So here they all go to the eye, to this single viewing point, and there all the lines are parallel, so everything remains consistently measurable. And there are various kind of attempts to think about that in terms of what that actually means in the world. Perspective machines, the one on the top is just basically a grid, but you notice that the artist is looking through to see the model who is drawing, but you notice that he has in front of his eye a sort of stick, a gnomon, and that's defining his viewpoint, so that whenever he looks at the model through the grid, he's always looking from the same position. Because if you move to the left or right, you get a slightly different perspective. So to make it work, you have to look from the same point of view. And in the machine at the bottom, actual fact, the viewpoint is actually the nail on the wall. Because what this does is to take a piece of string to an object and then to mark with some kind of crosshairs where it intersects this frame. And then there's clearly this panel which flaps back, and then you mark that point and you trace, like join the dots, all the points to make a kind of perspective view. The key thing there is that it's about this kind of geometric relationship between a viewpoint and the thing in the world. As I say, conventionally we talk about perspective being invented in 1410 in Florence interestingly by an architect, Brunelleschi, and what he did was to draw the baptistry, and he drew it from a position standing on the steps of the cathedral, looking back at the baptistry. We don't know exactly what he drew, although people have attempted to reconstruct it, because the drawings he made don't exist anymore, so we don't really know exactly what he drew, or how he did it. But he certainly did something. And later on, Manetti described what Brunelleschi's experiment was like, or demonstration piece. And it's this rather peculiar thing where, in actual fact, the perspective view was painted on the outside face of this panel, and in the panel was a little hole, and you looked through the panel to a mirror where the perspective view was reflected. Any idea why Brunelleschi would do something as complicated as that to demonstrate perspective? And essentially what he's trying to do is find a way of making the viewpoint part of the demonstration. Because normally when you look at a perspective view, the viewpoint is absent. Vanishing point's there. The way the lines progress towards some kind of distant point, but the viewpoint, the point of view, is by definition not in the drawing, it's where you're standing. So Brunelleschi's demonstration piece is an elaborate way of actually kind of making a demonstration of how the viewpoint relates to the view. It also means that you can stand on the baptistry, on the cathedral steps, hold up the mirror, hold up the panel, look through, see in the mirror the perspective view, but you can also see it in the real scene, so you can see how it accurately correlates with the view beyond. and captures, incidentally, the clouds because he put mirroring on the surface of the picture, which reflected the sky, so that it had a real kind of dynamic sky. And this is somebody in the 1970s trying to make a reconstruction of that, which is a good way of working, actually, try and make reconstructions of things. And he also did some other demonstration pieces around different bits of Florence. As time goes on, the way of drawing perspective becomes conventionalized. So there become sort of sets of rules for how you draw perspective. And eventually many different kind of methods, if you like, for drawing perspective. But two particular kind of methods really stand out. One of them is Alberti's method, which if you've done a technical drawing of perspective, is probably something like what you used, or you maybe used the tier point method. But this is based on the idea that you effectively draw a section. There's the picture plane, there's your eye point, and you project from a kind of imagined grid viewed end on back to the viewpoint, and then that gives you the diminishing squares, as it were, which define a kind of tiled floor, and that kind of is the building block of it, as it were, for the perspective. And you do the same thing with other elements. You draw them in plan and in section in order to project them into perspectival space. And in this preliminary drawing by Leonardo da Vinci, you can see those lines drawn there within the drawing, and the vanishing point there right at the back, which results from that. And in a painting like this, which you can go and see at the National Gallery if you're interested, clearly that set of rules creates the space within the painting. This is a space defined by perspective. However, when Serlio, a bit later on, was describing the two kind of key methods of drawing perspective, this was not as you might expect, the method that he was proposing to be used by architects. This was the method he said was for artists. And the reason for that is that it doesn't create it's not based on constructing a drawing from a kind of proposed building or a kind of orthographically defined geometry. Rather, it's a bit like creating a stage set. So the space is created within the painting and defined or made visible by the architecture and the tiled floor and so on. But actually, it's just really a kind of stage in which then characters and stories and so on can be played out. A lot like the kind of stage sets of the time. Has anyone been to Verona? No, sorry, not Verona, Vicenza. Anyway, Teatro Olimpico in Vicenza, where it's based on that principle. I might even have a slide of it. This is another kind of curious thing by Borromini, which is a piece of architecture that then uses those kind of principles to make a space which is distorted according to the rules of perspective. So when you look at this space, it looks like it's much longer than it actually is because everything gets smaller as it goes further away. So, this statue at the end of the colonnade looks, when you're standing looking down the colonnade, like it's a sort of life-size statue, but in fact it's only about 70 millimetres high. But the whole thing is a kind of stage illusion built in architecture. Yeah.
I've heard that in Hollywood, the early Hollywood, there was lots of Italian painters painting sets because they come out of this amazing tradition of kind of faking reality.
Yeah, yeah,
It's
yeah.
just sort of an early version of VR, AR, whatever you call it.
Yes, because early cinema was a lot like theatre. It was stage sets, and they thought, because the cameras were very heavy, so you couldn't move them around easily. You know, like modern cameras are going on tracks and they can be going all over the place. But early cinema, you couldn't easily shift the camera, so you tended to design the whole thing around a particular viewpoint, so it was a lot like perspective. This is a different kind of perspective, and this is, ironically, this is the architect's perspective. This is the perspective for architecture. So, although it actually doesn't, in this particular case, have no architecture in it, what's going on here is instead of making a kind of stage set, although there is a little bit of that going on, some of these spears kind of point towards like some notional vanishing point. What's going on here is that all the things in this world have been projected into perspectival space. And the master of that was Piero della Francesca, who wrote a whole treatise on perspective. And once again, this is his, what Robin Evans calls his other method. And it ends up with things that, unlike the Crivelli painting we were looking at a moment ago, which seemed quite comfortable, you end up with these sort of slightly awkward perspectives as a result. If those of you who've kind of set up perspective views on a computer, if you take the 3D model and you look at it from different, sometimes you get some really weird views. It's just a kind of mathematical thing, and that's what's going on here. The reason that roof looks a bit weird is not because it's drawn incorrectly in perspective, but rather because the angle is just one that is not one that's kind of organised by perspective in the way that the Crivelli one is. And believe it or not, all of these heads are also drawn in perspective. What Piero did was to measure heads. So he took real heads, real people, and kind of plotted the geometry of the head as if it had as if he was drawing like a series of orthographic views through the head, and then he projects that into perspectival space in a way that is not hugely dissimilar to what actually happens in a computer. And Robin Evans, who studied this, whose books on drawing and articles on drawing you should definitely have a look at, tested this out by reverse engineering the perspective, if you like. So this is a painting by Piero with a series of figures in, and strangely they all look very similar, and that's because you're not going to go around measuring that many heads, let's face it. It takes a while to measure heads. So once you've measured one, you use the same head again and again, which is why they all look the same. But he demonstrates that it's not just looking a bit the same, they are literally the same in terms of the dimensions of the distance between the eyes and the nose and the mouth when you take it out of perspective space and look at the real dimensions that those things would have. Later on, perspective reduces then to this sort of idea that what you're looking at in the world is really defined by that kind of retinal image, that somehow, in fact, your understanding of the world is this kind of perspectival view, ignoring the fact, for example, that we have two eyes and that we move around, and there's all sorts of reasons why perspective is kind of abstract, but it's kind of increasingly pushed to its limits, including this box by Van Hoogstraten, which used to be on display in the National Gallery. I don't think it is at the moment, but it does a similar thing to Pozzo, and it wraps the perspective view around the inside of the box, across the floor and the ceiling of the box, not lined up as a painting of a box interior, but with the view cutting across the interior of the box, if you like, and you view it from particular viewing points, and it looks kind of correct. This is another, perhaps slightly better example of that kind of thing, which of course is part of a tradition of kind of Dutch painting in the 17th century. All of this is kind of what's known as anamorphosis, which is this technique for projecting perspective onto unusual surfaces, I suppose, onto planes other than one perpendicular to the view. This is again in the National Gallery. It's a painting of two ambassadors, and there's all sorts of symbolism in the objects and so on that are arranged on the table behind them. But in the foreground is this kind of ominous smudge. And in fact, when you look at it from the right angle, what that smudge becomes is a skull. And it's obviously a comment on something that's going on in this little diplomacy here. But apparently also it was meant to be, one of the theories is it was originally designed to be viewed on a staircase. So on the side of a stair. So as you were walking up the stair, you got this really kind of oblique view of the painting, and then you saw the skull. Which is exactly what's going on in Pozzo's interior. It's that kind of distortion of the perspective view wrapping around the various kind of surfaces to make the perspective view. So that was one painted interior. The next one is a much smaller space. This is, as we've already said, a little painted interior by Theo van Doesburg. It's actually a room for preparing cut flowers. It doesn't have much to do. It's the space where you bring the flowers in from the garden and prepare them. And it was, we've said before, it was painted by Theo van Doesburg, who is a famous De Stijl artist from the 1920s in the Netherlands, and made a lot of these kind of abstract geometric compositions around that time. So he was invited by the owners of the villa to paint the interior of this little room. As it turns out, he never actually went there, so he didn't go and see the painting that got produced. He just sent kind of instructions for how it should be painted. There's the little room there, and it's just adjacent to the garden in the villa, and so it's a fairly small space and in theory quite insignificant. But the painting is worth examining in a lot more detail, and there are various properties of it that we can begin to analyse, including the use of the diagonal. So these are the painted surfaces of that room, and you can see that each of the walls is defined by these patterns of diagonal lines and coloured planes, which are typical of Van Doesburg's kind of style of painting, if you like. There they are on the surface of the wall. And there's the drawing that Van Doesburg did to describe this interior so that somebody else can paint it. And you can see those diagonal lines cutting through the drawing in various different directions. It's interesting to note also that it's not the way he's drawn it on the paper. Do you see that? You would think that the drawing would be aligned with the paper, but in fact it's also drawn at a diagonal, which is part of his theory too, which is that these kind of counter-composition paintings that he did were meant to be kind of displayed in this kind of way. So instead of the painting being displayed horizontally, you twist it at 45 degrees and display it like that. So the lines in the painting become aligned with the plane in which you occupy, if you like. And he begins to associate the diagonal with a kind of spiritual dimension of something which is kind of extended beyond human world. He also worked a lot with what we might broadly call axonometric, so doing drawings like this. And you can, when you start to look at these two things together, you can see how some of those diagonals from axonometric start to make it into the composition of the painting. So the diagonal is not just a way of, an arbitrary way of dividing up the surface to make these patterns. It actually has a lot of meaning for van Doesburg in various kinds of ways. On top of that, there's also another aspect of this which is defining what van Doesburg is trying to do here. On the left is a little sketch by van Doesburg, not for the painted interior, but just a kind of painting that he was working on or something. And he called this a tesseract study. And on the right is a drawing by a Dutch mathematician around the same time, describing what had previously been named by a English mathematician a tesseract. And a tesseract is a four-dimensional cube. So the fact that van Doesburg called this a tesseract study, and the fact that there are kind of formal similarities with the kind of drawings that we find here, suggest that what he was trying to do was in some way to explore this idea of a four-dimensional cube in the three-dimensional space of the little flower room. Drawing four-dimensional cubes, as it turns out, is quite a tricky thing, because a four-dimensional cube is not, as you might think, to do with time. Later on, Einstein came up with his theory of relativity, and people started to associate time with the fourth dimension, because that's how the geometric model that Einstein used for general relativity was time as the fourth axis. But here we're talking about a kind of earlier idea, which is a kind of fourth spatial dimension. So we know there's this kind of direction. I can move that way. I can move that way. I can also go up and down. At least I could if I could levitate. But there's no other directions. There's only three directions in the world we inhabit. But in this mathematical world, there are four. So there's another dimension which we're unable to perceive, which can be described mathematically. And therefore drawing it is quite tricky. And this is another van Doesburg attempt to use axonometric to try and capture some of that. So what we're looking at here is the various faces of a four-dimensional cube, kind of distorted and twisted to fit into three-dimensional space. This is how the theory of the fourth dimension can be described. It's about the mathematical consistency. Now, you need to cast your mind back to Pythagoras' theorem that we were talking about earlier. In fact, the first equation looks a bit like Pythagoras' theorem. But in this case, it's not. Does anybody know what the formula at the top is? Any mathematicians in the room? I think perhaps not. Okay, so that is the formula for a circle. X squared plus y squared equals 1 is the Cartesian formula for a circle. And it's based on Pythagoras' theorem. So if you imagine imagine the hand of a clock going around sweeping out a circle, as that hand of the clock moves around, it describes a kind of right-angled triangle that pinpoints the point on the circle. So that's why it looks like Pythagoras' theorem. It is effectively Pythagoras' theorem. So if you plot all the points, changing the angle, what you describe is a circle. I should do a drawing of that too, really. But anyway, what about the second formula? Any ideas? Yes?
Sphere.
Yes, you've done this before. So the second formula is a sphere. And the difference, of course, between the first formula and the second formula is that it has an extra dimension. So x squared, y squared is a two-dimensional shape, a circle. X squared plus y squared plus z squared defines a three-dimensional surface, which is a sphere. So now, what about the third one? four-dimensional sphere. Someone said it. Yeah, it's just about extending the pattern. So you can describe a two-dimensional sphere, which is a circle. You can describe a three-dimensional sphere. So why not just keep following the same pattern? And you could keep going. You could have a fifth-dimensional sphere, a sixth-dimensional. You have no idea what these things would be like. What would a four-dimensional sphere be? That's a trickier question. But describing it mathematically is easy. And in fact, the formula at the bottom is the general formula for a sphere, if you like, which is taken to the nth dimension. So you could take it to any number of dimensions. Or to look at it a different way, graphically perhaps, if we take a point and we project it unit distance, we get a line, which is one dimension. Point is 0 dimensions, line is 1 dimensions. If we take the line and we project it unit distance, what we get is a square. So that's a two-dimensional shape. And then if we take the square and project it unit distance, what we get is a cube. But something has already happened here, and that's that this drawing, this screen, is two-dimensional. So, of course, the cube doesn't fit in the drawing, does it? Unless it was a 3D cube, like a model. And we're having to cheat. And the way we cheat is to squash one of the angles. So here, these right angles are real right angles as they are in the cube. But in this illustration, in this axonometric illustration, this angle's been distorted. Do you see that? So that's a right angle. That's a right angle, and that's a right angle, and that's a right angle. But this angle, going backwards, has been squashed to fit in the plane of the paper. That's smaller, that angle is smaller than 90 degrees. Although we know in the real cube it would be 90 degrees. But in the drawing, it's been squashed. So if you take that same principle and you project the whole cube unit distance, what you get is a four-dimensional cube. And it has all the right mathematical properties. It has the right number of surfaces. It has the right number of points, lines, and so on. But it just doesn't fit into three-dimensional space in the same way that the three-dimensional cube doesn't fit into two-dimensional space of the paper. So how do you investigate this thing that you've created? Well, one of the ways might be to cut slices through it. We could understand a three-dimensional cube maybe by cutting slices through it and looking at its two-dimensional sections. So you can do the same thing with a four-dimensional cube. You can cut it into cubic slices. So you cut up a cube and you get squares. You cut up a four-dimensional cube and what you get is three-dimensional cubes. So there's a whole series of those, and a mathematician named Charles Hinton in the 19th century, really, but then into the early 20th century, did these sort of thought experiments where he put together these descriptions of four-dimensional cubic sections and colour-coded all the pieces, so that the idea was that you could try and learn all the associations between these pieces in the four-dimensional cube and eventually begin to develop an intuition for four-dimensional space, that you could, in a sense, learn to perceive four-dimensional space by rehearsing the properties of the cube, and he called this a tesseract. Another way of trying to illustrate it is a kind of developed cube. So this is both something that happens in Van Doesburg's drawings, but also in the mathematicians of the time. And this is the idea that you can fold it down. So if you take a cardboard box and you cut the sides, you can fold it down flat. And what you end up with is a sort of cruciform shape with the sides folded down, on square sides folded down. So you can do the same thing with a four-dimensional cube. You can take the sides, which are in this case cubes, and you can fold them down into three-dimensional space and get this kind of cruciform thing. Which is not only interesting for the fact that Van Doesburg is drawing this kind of thing, but is also interesting if we go back and think about that drawing that he did of the flower room, where what he seems to have done is to fold down the walls of the room into the drawing in order to paint it. So there's the same thing going on there as well. These are some more Tesseract studies again. Van Doesburg set against a mathematician on the right who doing some very similar kinds of drawings. And then if we go back and look at Van Doesburg's paintings again, can also begin to see how some of this starts to fall into place. And these planes existing in this kind of strange axonometric depthless space are also perhaps attempts to describe the four-dimensional cube or something, some kind of construction in four-dimensional space. And when we look at his compositions, it's possible to begin to see these diagonal lines not just as diagonal lines written on the surface of the wall or cutting across the surface, but actually kind of edges of imaginary cubes extending in pictorial space beyond the surface of the wall. So development that we've just talked about, this idea of folding down, was something that came out of descriptive geometry in the 19th century and is really just all about this kind of folding or unwrapping of surfaces. Some things are, this is called development, some things are developable, and other things are not developable. One of the things that's developable is a cone, so you can unwrap that and make a flat surface, but other shapes or cylinders you can do. Actually, mostly ruled surfaces can, but not all of them. And of course, it's a convention that has been used in architecture for a long time. But there's actually one fundamental difference which is worth exploring between the way Van Doesburg does this and the way other architects of the past had done it. This is a drawing by Robert Adam for Osterley Park, and essentially what he's done is to draw the plan, as you might expect, and then fold the walls down from the plan. So the folding is happening at the floor level. So these surfaces are being flattened down. As it turns out, with Van Doesburg, it's not quite that simple. Similarly here, we have a kind of attempt to capture the ceiling in a plan view, which is what Van Doesburg's doing there. And in this case, this is done again by Robert Adam as a reflected plan. So do we know what a reflected plan is? Anybody done that? It's like when you draw the ceiling, but not looking up. You draw it like it's been projected down onto the floor, or as if the floor was a mirror. So, but again, as it turns out, this is not actually what Van Doesburg was doing in his drawing when he drew the ceiling. So the key thing now is to know that, as I mentioned before, that he never went to the site to supervise the painting and never went to look at it, as far as I'm aware. But he sent the drawing, and the painters had to try and interpret his drawing. So what they did was assume that what he was doing was a reflected ceiling pan. So they painted the ceiling, as you can see, this is as it was painted, as if that was the reflected ceiling plan. But that wouldn't really work in terms of these walls, because the walls don't seem to be folding down from the bottom edge. You can see there's the window there, and there's the window there. The walls are not folded down like in the Robert Adam drawing. They seem to be folding. They seem to have been flipped the other way. Art historians have dismissed this as Van Doesburg not knowing what he was doing, which may well be true. But to give Van Doesburg his credit, most of what he did is quite intentional. There's not much accident really in what he does. So maybe there are other kinds of explanation. The fact that Van Doesburg didn't know what he was doing, supposedly, means that it was assumed, therefore, that the ceiling was meant to be actually the other way around. That actually it was meant to be a view up, and the walls were folding up rather than being a reflective view around there. So, I mean, this is what the ceiling looked like when it was originally built. It got into a bad state, as you can see, and later on it was restored. And they tried, when they restored it, to put it right. So they corrected it. We'll see that in a moment. Van Doesburg did other kinds of, or I should say that one of the reasons why it's kind of assumed that this way it was painted was wrong was because in the drawing that Van Doesburg did, the diagonal lines kind of follow from the ceiling to the wall. Do you see that? There's a sort of extension of those diagonal lines, so it becomes a continuous pattern. But the way it got painted, they don't. There's like this breakage here because the pattern doesn't continue. We could look, to try and get an understanding of what's going on, we could look at some of Van Doesburg's other works. So this is an interior of the Albert Cinema, and you can see there are patterns that don't continue. So perhaps, actually, that's what he meant. It was not supposed to continue. So that's one theory. But when they restored it, they tried to fix it, so now they do. So they swapped over, they reflected the ceiling back as if it had been a view up, and now the line's kind of continuous. However, there are potentially other ways of looking at it, and various people have looked at this, including myself, and there are various different attempts of trying to correct the drawing and draw it as it should have been. But if you actually, believe in this idea that actually it wasn't a view, reflective view, but a view looking up, there are problems too. So we can see in Van Doesburg's drawing that the plan actually contains this edge of the window which lines up there, and that would suggest, well, if we go back and look at the original plan, that's the right way around if you're drawing a plan. Whereas if you were drawing a view up into the space, the floor plan would get reversed as well. So in fact, the room would have been drawn the other way around. So that bit that defines the edge of the window there, and this bit that defines the door, it would all be, because they're unequal on either side, that bit there would be the other way around. So clearly what Van Doesburg's doing is not either a view up. Then you look at this, and you see something that's different again. Here, there is a kind of drawing, or turns out it's a sort of maquette of, again, one of those cinema dance hall interiors. And this is a drawing that he made himself and was in his office on site in the Albert, and you can see that drawing there propped against the wall. But you can also see in there that it was a drawing that was meant to be folded. Can you see that? There's sort of folding, it's folding around those edges. So it's not so much a drawing perhaps as a kind of model or a maquette, with these edges being foldable. And the way they're folding in that drawing is not down around the ceiling. So it's not like the drawing is, you turn the drawing upside down and flap the walls down. They're folding seemingly around the outside of the box. So it's like he's doing that. So the drawing is not the inside but the outside, and then projecting it into the interior. And so now we have kind of three options. There's what actually got built, there's the restored interior, And then there's this one, which is potentially the one it was supposed to be. So when they restored it, they actually corrected the one thing that was right, and left all the things that were wrong, which were the walls. Of course, nobody really knows. But the nice thing about this solution is it fits with his drawing and doesn't require there to be a mistake in his drawing. And it also ensures that there's continuity of the pattern across the edges. So that's what I believe, anyway. There's also another, I won't go through this with any detail because we're completely out of time, but there's also a whole argument around axonometric sections and thinking about how slices through things in axonometric might be, again, one of the ideas behind the patterns that he put onto these surfaces. So this is, again, a drawing by a Dutch mathematician, and this is Van Doesburg's painted interior, and you can begin to see that there are kind of similarities there as well. So there you go, two painted interiors, one defined by perspective and the other defined by not only axonometric, but also potentially a whole set of ideas about four-dimensional geometry. And that's about it.
Thank you very much. Are there any questions for Richard before we let him go? No? Nobody's got questions?
That's fine.
I mean, I think what I didn't say at the beginning is that this is a language. It's a language of describing, it's got its own syntax and so on. So it kind of locks into sort of Lacanian idea that everything is written in language that we do understand. And that is to do with invention. So as you invent new tools, new possibilities open up. So again, how you sort of look at the space and how you understand the space is following our discoveries in mathematics or observation and so on.
I think and it also makes you, I would encourage you to think more carefully about how you choose to draw something. Because the way you choose to draw something is not just about illustrating it. It's not simply about communicating what it is you're proposing. Actually, the way you choose to draw it informs what you're doing. So, if you choose to show something in perspective, why have you chosen that as a convention? What is it about the thing that you're drawing that makes it kind of susceptible to representation in perspective? And similarly, if you choose to draw it a different way, think about the conventions that you're using and how they relate to what it is that you're designing. But also, there's this kind of thing about, it's a kind of chicken and egg thing, really, about, we see the world and interpret it and describe it, whether that's through geometry or philosophy or whatever. But then that whole system can kind of work in reverse. So the way we choose to describe and conceptualize the world can inform the things that we make and the things that we produce. So when Marshall McLuhan said a piazza for everything and everything in its piazza for the Renaissance, what he was really getting at was not just that everything was organised in perspective, but that a whole way of conceiving space and an idea about the relationship between the viewer or the subject and the world was being reflected in the architecture that was being produced. And potentially the architecture could change it as well. That's another thing. The architecture could be a vehicle for shifting the way you understand your relationship to the world.
But it's quite interesting when you describe this fourth dimension. I was reading a kind of a popular physics book during the summer, and he was talking about the fourth dimension. I just I couldn't understand it because I couldn't see it, and yet it was kind of quite obvious, how it works. So it's kind of imagined spaces that we know through mathematical equations can definitely exist.
Mm-hmm.
But it's this sort of our inability to see it and to visualize it, because we are obviously imbued with, this reality of the world and how we see it.
Our perception of the world is...
Yeah, it's incredibly powerful, because, you can't, unless you trained your mind to try and envisage these things, you can't really do it.
Yeah, again, there are kind of two ways of looking at that. That our understanding of the world is a result of the environment that we've evolved in, which is essentially a three-dimensional kind of... The other idea is that actually it's just that our perception creates that world for us. That we see things like that because that's the way our perception works.
Okay.
Right, okay,
All right,
good.
thank you, Richard. Thank you very much for that. I know that you've got a busy schedule, so I'd really appreciate it.